In this lecture, we will be introducing the concept of conditional risk management. Recall that we have a model called the GARCH-ARIMA model for a time series. So if we take epsilon t being a white noise 0, 1 process for our innovations, a time series xt is said to be a GARCH-ARIMA process if you difference xt d times to get a stationary process yt, and that yt is an ARIMA process with GARCH noise terms. So our GARCH noise term is given here by AT. We see sigma t handles the variance properties for the noise term because epsilon t is standard in that it has mean 0 and variance 1. And sigma t, that conditional standard deviation, has memory of previous values of the noise terms going back qg time steps and previous values of the conditional variance going back pg time steps. We then have our ARIMA, autoregressive moving average model, for yt here. And so we see the autoregressive portion where you have memory of previous values of y going back pa time steps, and we have memory for previous noise terms going back qa time step plus our new noise term. So this is our model, a model for stationary time series where the GARCH noise term builds in conditional heteroscedasticity. And so by that, we mean we will have a non-constant conditional variance, namely as defined by this equation 1 for the conditional standard deviation. We now consider the concept of the conditional loss distribution. So if we have loss L adapted to our filtered probability space omega fp and our filtration ft, and remember the key thing for a filtration is that we think of ft as the information available at time t. With this setup, the conditional loss distribution, we're writing this notation here, capital F will be a CDF. So the CDF of the loss distribution for holding period over time t to time t plus 1, as written here, given the information available at time t. So given f sub t is defined as the following. So our CDF, our conditional loss CDF, is the probability that the loss at time t plus 1 is less than or equal to little l given the information at time t for little l in R. So the setup in which we will use time over time t to t plus 1, and so we think of it in the usual way that we are standing here at time t, that's the present, and we're modeling an uncertain future at time t plus 1. Our portfolio loss time over time interval t to t plus 1 is lt plus 1, and our portfolio value is vt at any time t, and our risk factor change is the log return of the portfolio. We write that as xt plus 1. So that's log return over this interval of time. And then if we look back at our previous work, we, in such a case, derived that the linearized loss over this time, so the linear approximation to the loss, is negative vt times xt plus 1. And again, we can write our information, the sigma algebra we will use, or the filtration we will use, will be at any time t, our information is that garnered by observing the risk factor changes up to the current time t. So in this framework, we want to compute a value at risk and an expected shortfall for the conditional loss distribution. And the important thing to notice is that this is different than the unconditional loss distribution. The conditional loss distribution is saying, in this case, if you're looking at time t plus 1, we are using the information that we can observe up until time t to compute a value at risk and an expected shortfall that will be different than if we did it for the overall loss or linearized loss without taking into account the information contained in that filtration. Without loss of generality, let's assume that the portfolio value starts out at 1. And of course, if you're implementing this, you can just take your initial portfolio value and normalize it. And that implies that the linearized loss, right, remember there's a VT here. So our linearized loss is given by this expression. That VT becomes a 1. So our linearized loss just becomes the negative of the risk factor change or the log return on the portfolio. Now let's assume that our linearized loss process is adapted to the filtration. And remember, that simply means that at time t, you have enough information to be able to determine the value of your linearized loss. So remember, the idea of a stochastic process being adapted to a filtration just means the filtration gives you the information you need to be able to observe the value of this stochastic process as time moves along. And we're going to assume it follows a stationary model of the following form. So the linearized loss at time t is equal to some mu t plus sigma t epsilon t, where mu t and sigma t are ft minus 1 measurable. So that means, notice the key here is ft minus 1 as opposed to t. So this means that we can observe or compute mu t and sigma t at the previous time t minus 1. Epsilon t will be our white noise process, our innovations, and those will have cumulative distribution function g. And we're setting this up with it in mind that we want to use our ARIMA GARCH model. And if we set LT, delta, our linearized loss process, to be an ARIMA GARCH model, all of these properties are satisfied. And in that case, mu t will be the conditional mean of our process. And the ARIMA part is handling that conditional mean. And then we have sigma t, which is our conditional standard deviation. And this is handled by the GARCH part. And this is a very nice model for portfolio or asset returns because the key typically in financial data is we want to be able to have this conditional heteroscedasticity of a time-varying conditional standard deviation. The conditional mean is also nice to model, but in financial data, this tends to be more stable than the conditional standard deviation or variance. We tend to see periods of market quiet and periods of high market volatility. And the key in this type of model is that our conditional standard deviation can pick up on that. So let's look and see in this model, what our conditional loss CDF actually looks like. So the conditional loss CDF evaluated at L, by definition, is this conditional probability that the linearized loss is less than or equal to little l given the information at ft. Using our model, we have said that this linearized loss can be written as mu t plus 1 plus sigma t plus 1 times epsilon t plus 1. So we replace the linearized loss at time t plus 1 with this expression, and this is less than or equal to L given information at ft. We then note that we can drop the conditioning because epsilon t plus 1 is independent of ft, or rather uncorrelated with any random variables that generate information in ft. And sigma t plus 1 and mu t plus 1 are ft measurable. So this becomes the probability that mu t plus 1 plus sigma t plus 1 times epsilon t plus 1 is less than or equal to L. And again, because our epsilon t plus 1 is independent of the sigma algebra, and mu t plus 1, sigma t plus 1 are ft measurable. That's kind of the whole point of the ARIMA modeling, is that we can use information at the previous time step to model things happening at the next time step. We then z-score this, so we have the probability that epsilon t plus 1 is less than or equal to little l minus mu t plus 1 over sigma t plus 1. And this, by definition, is the CDF of that epsilon, which is equal to g of that z-score, L minus mu t plus 1 over sigma t plus 1. And so we see that in order to get the conditional loss distribution CDF, we have our conditional mean and conditional standard deviation coming from the ARIMA model, the ARIMA-GARCH model, and we are feeding that z-score to the CDF of the innovations, the epsilons. And so we have that repeated here. Well, then the goal is to come up with value at risk and expected shortfall calculations for this conditional loss distribution. And we use a superscript of t to denote that it's a conditional expected shortfall and a conditional value at risk. Now you have to be a bit careful with the terminology here. When expected shortfall was first introduced, it was actually called CVAR, which is short for conditional value at risk, which was poorly named because this value at risk for the conditional distribution is not expected shortfall. It's just a value at risk using this conditional distribution. And similar derivations to that of value at risk and expected shortfall for an unconditional normal loss distribution, which we have covered in earlier lectures, yield these results. So our value at risk for the conditional distribution at confidence level alpha is the conditional mean plus the conditional standard deviation times the quantile function of the distribution of the innovations. And the expected shortfall for the conditional distribution at confidence level alpha is the conditional mean plus the conditional standard deviation plus the expected shortfall at confidence level alpha for a random variable with the CDF of the innovations. And recall what we're actually doing here. If this is your loss density, then your value at risk at confidence level alpha is this loss here that occurs when you have, this is 1 minus alpha area under the curve. And our expected shortfall is the average loss restricted to this yellow area. So given that you're in that yellow area, expected shortfall is the average loss you can expect in that area. And these are simply the expressions that we get when we do this type of modeling for a conditional loss density. The concept for expected shortfall and value at risk, they don't change in this model. It's simply that our distribution is different. And our distribution is this conditional distribution where we are using the information up to time t to inform our estimates of what's going on at time t plus 1. If we go to the case where the innovations are normal, and so the innovations, recall, are the epsilon t's, so if those are standard normal, then because we have closed form expressions for value at risk or the quantile function, so we have the quantile function for our epsilon being the inverse of the normal CDF, and then we have expected shortfall at confidence level alpha for that epsilon, where phi is the PDF of the standard normal distribution. So in the case where our innovations are assumed to be normal, we have these closed form expressions for our value at risk for the conditional loss distribution and our expected shortfall for the conditional loss distribution. So this gives us a way to do this type of model, and we can take our data for our loss distribution, use this type of model. So if we actually take, say, for instance, daily losses, we use a routine to fit our GARCH model to those losses. Typically, we assume from a modeling perspective that losses are stationary. So we probably wouldn't be differencing this. If we see enough autocorrelation, we may difference it once. But let's say we don't difference it, then we're doing d equals 0. We model our losses as this ARIMA. We fit that using a maximum likelihood routine, which is separate from this lecture. And then we are able to risk manage in time using these formula for the value at risk for the conditional loss distribution and the expected shortfall for the conditional loss distribution. In the normal case, things are even nicer.